while maybe since we considered concavity, but remember what concavity is all about. The second derivative tells us about concavity. All right, and to be concave up, the second derivative, well, the second derivative must be greater than 0, positive. So I'm looking for where, according to t, the second derivative is greater than 0. So this is a second derivative problem here. We need to come up with our second derivative off these parametric equations here that we have. All right, well, starting off then, find the second derivative, we need to find the first derivative, dy dx, y prime. Well, dy dx in terms of parametric, well, you do the derivative of the y, which would be 2t, over the derivative of the x. With respect to t, so it'll be 3t squared minus 3. Then for our second derivative, which the book likes this, I like then, well, since it's a parametric equation, what it's going to work to be is the derivative of the d of y prime dt over dx dt. Or in other words, this is my y prime, so I need to take the derivative of that and then divide that by dx dt. That's what I need to do. So I need to take the derivative of my first derivative and then divide it by dx dt again. All right, so again, that's quotient rule. Low, derivative of that would be low, 3t squared minus 3 times d of the high, which is 2, minus high, 2t, derivative of the low, which would be 6t, over low squared. And then divide that by dx dt, which is just the derivative of x with respect to t, so it would be 3t squared minus 3 again. This would be my second derivative. Well, that's going to be, what, 6t squared minus 6 minus 12t squared over 3t squared minus 3 squared times, well, divided by 3t squared means times 1 over 3t squared minus 3. So my second derivative winds up being negative 6t squared minus 6 over 3t squared minus 3. And notice I've got, that's cubed now. All right. So we are going to want there where we're wanting concavity up. So I want to know where that's greater than 0. Well, to start with here, what I'm going to need to find are where it equals 0. First of all, set that equal to 0, and that'll find the critical values, the values where we'll have changes maybe in concavity or whatever. So I'm going to set that equal there to 0. 6t squared minus 6 negative, second derivative, 3t squared minus 3 cubed, set that equal to 0, and this will give me my critical values for second derivative. All right, well, that's going to be pretty nice there. Really just multiply by 3t squared minus 3 to the cubed, and that'll just give me 6t, negative 6t squared minus 6 equals 0 times 3t squared. Cubed, but multiplied by 0, that's still 0. So negative 6t squared minus 6 equals 0. Let's see. I think here, just about everything by negative 6, so that gets me t squared plus 1 equals 0. Well, that, as far as real values, no real solution. Okay? But what else can be critical values? That doesn't give any critical values, but remember, we can also have critical values where the denominator equals 0, or where the second derivative does not exist. So 3t squared minus 3 cubed, that can also set up a scenario for critical values. And I think cube root both sides, we get 3t squared minus 3 equals cube root of 0, 0. Yeah, that's going to be, that is going to have some solutions. Add 3, divide by 3, t squared equals 1. So that's t equals plus or minus 1. And so that's, as if you will, kind of the division point, a division line for my critical values, two division lines. So I've got either negative 1, t equals negative 1, or t equals positive 1. Now I just need to figure out, I want where the second derivative is greater than 0, which I just erased there. Second derivative. It was negative 6t squared minus 6 over 3t squared minus 3 cubed. All right, so if I plug in, just test to see where the second derivative is positive or negative. I think we should try in here. Let's see, 0 would be in there. So we have 0, so it'd be minus 6 over negative 3 cubed. Yeah, that's going to be a positive 6 over 27. And so, I've got concave up right in there. And I think on the other sides, if you do 2 and try 2 and negative 2, I think you'll wind up with, negative values. So these are concave downs in these ranges here. So, for what values of t is the curve concave up? Well, it's concave up when t is between negative 1 and positive 1. So anyway, just wanted to throw that at you. It's been a little while since we talked about concavity. All right, we talked about derivatives, slopes, concavity. What about areas and parametric curves? Okay, well, for a Cartesian curve, y equals f of x, when we talk about areas, we're talking about area under the curve, and that is the integral, right? We're talking about between the curve and the x-axis. It's the integral from a to b of f of x dx. That gives me the area under the curve. Could be between the net area from A to B. Well, if we have parametric, well, let's think about parametric for just a second. In parametric, we're going to have an x equation and a y equation. X is going to be some function of t, and y is going to be some other function of t. Well, just from this one here, here's what we're going to have to utilize here. If I'm talking about this, my x prime, or dx dt, let's call it. Well, that's the derivative of x with respect to t, which in this notation here, we could just say is f prime of t, just the derivative of that particular expression. Why do I mention that? Well, it's because what I'm going to do is I'm going to use, area under the curve between the curve and the x-axis. I've got this dx. Well, dx, one thing about it is it's going to have a counterpart here in terms of the differential dt. So what would that be? Well, just multiply both sides by dt. And so dx is the derivative of the f, the x function there, in terms of t, times dt. Okay. All right, so here's where we get this area. If we're talking about parametric curves, x equals f of t, y equals g of t, then the area from t equals alpha to t equals beta, instead of using a and b, since we're using t's now instead of x's, we're going to use our t upper limits and lower limit, alpha and beta, for just the way they do it. Okay? The area then from t equals alpha to t equals beta between the curve and the x-axis, it's going to be found, well, let's think about it here. We know that the area is the integral from a to b of f of x dx, or y dx. Well, don't I have, then, I do have something for y, it's g of t. Dx, since again so now I'm converting from y's and x's to t's, parameter t's, in terms of t. Well, that's what we just talked about. The dx, remember what it was? It was f prime of t dt. In other words, this derivative times dt. And so now I've gone from x's, if you will, to t's. So my upper and lower limits also need to be in terms of t. So I've gone now to alpha and beta. So this is the area under the curve in parametric form. It's the integral from alpha to beta in terms of t, g of t, f prime of t, dt. So this is the area under the curve for parametric equations format. Okay? So let's do one. So what does it work out to be? Well, you take your y equation times your derivative of your x equation in your parametric format there, and then from whatever t values you want to. So it's the straight up y equation times the derivative of the x equation. All right, so let's do one. Find the area from zero is less than or equal to t is less than or equal to 2 pi for x equals t minus sine t, comma, y equals 1 minus cosine t. All right. So the area here is a integral from alpha to beta. All right, so alpha is 0, beta is 2 pi. So 0 to 2 pi of g of t, which is your y function, 1 minus cosine t, times f prime of t. Well, f of t is the x function, so we do f prime. What is f prime? F prime is going to be 1 minus cosine t. So that's what I put here. I don't put f of t, I put the f prime, and then that's times dt. So this is the integral. That would give me the area for this curve, 0 to 2 pi. How do I do this? Well, this brings back our old friends, the trig integrals. On this one, I think the best thing to do would just be go ahead and multiply that together. So we have a equals 0 to 2 pi. Pull that out, it would be 1 minus cosine t minus cosine, that would be 2 cosine t, plus cosine squared t, which a couple of those would be very easy. The integral of 1, so I just divide that up, 0 to 2 pi. So I have the integral of 1 dt, that's going to be easy, minus basically the integral of 2 cosine t, that'll be easy, plus the integral of cosine squared t dt. That's going to take a little bit of work. All right, so what about this integral? This would be integral of 1, that'd just be t, with respect to t. The integral of 2 cosine t, well, that's just a straight antiderivative of cosine, antiderivative of cosine sine, so it'd be minus 2 sine t. But that leaves us this one. Remember what we do there? Cosine squared integral? Well, that one is one, if you remember, we have to use our old friend, the double angle identity. For cosine squared t, remember the double angle says that is, well, it's 1/2 times, we usually wrote it 1 plus cosine 2t, or 1/2 plus 1/2 cosine 2t. Yeah. So we're going to do the integral of 1/2 plus 1/2 cosine 2t dt. Which that antiderivative is easy. 1/2, the antiderivative is 1/2 t. The integral here, that's just a u substitution. U equals 2t du equals 2 dt divided by 2 du over 2. All right, so this would be plus, then I got the integral of 1/2 t is 1, the integral of 1/2 is 1/2 t. The integral of 1/2 cosine t, so that would be the integral of 1/2 times cosine of u du over 2. Yeah, that's just 1/4 cosine u. So the antiderivative, so we have t minus 2 sine t plus 1/2 t plus 1/4, the antiderivative of cosine is sine of u, but u is 2t. So 1/4 sine of 2t is what I get there. And now, remember, I'm doing a definite integral, 0 to 2 pi. A little bit of work to get there, but that's what it is nonetheless. Okay? All right, well, let's see what we get here. Plug in 2 pi, so we have 2 pi minus sine, minus 2 sine of 2 pi plus 1/2 pi, 1/2 2 pi, sorry, and then 1/4 sine of 4 pi. And then the good news is, plug in 0, that's 0, sine of 0 is 0, that's 0, sine of 0 is 0. All right, so the rest is 0. Everything else is 0. All right, so we've got 2 pi. Sine of 2 pi is 0, so that's 0. That would be pi. Sine of 4 pi. Sine of 4 pi is 0, so that's 0. So that's just 2 pi plus pi. It's 3 pi. So the area here is 2 pi. All right? Now, what that does give us is the area from 0. So that is the area, we call it under the curve, but it's the area swept out by this particular curve. And so let me see what this looks like here. T minus sine t and 1 minus cosine t. See what that looks like. All right, we're going from 0 to 2 pi. And okay. So yeah, this is what this looks like. See if I can square that up. I think it's kind of a half circle there.